Okay, thanks for your patience for the interrupting. Hello, everyone, and welcome back. In this section, we dive into one of the most critical aspects of making Federated truly effective. It comes to the client-side adaptation. My name is Zhiwei Li from UTS. And over the next about 30 minutes, we will explore why adaptation is necessary and how various techniques allow us to personalize the recommendations within the FL framework. So let's start by briefly revisiting the standard FedRAC framework, often built upon principles like FedAVG. As you recall, the core idea involves clients, typically users' devices, training recommendation models locally on their private interaction data. These local updates, typically gradients or model parameters, are then sent to a central server. The server aggregates these updates often by the averaging to create an improved global model, which is then distributed back to the clients for the next round. This iterative process allows collaborative training without sharing raw user data. However, this standard approach faces a significant hurdle. The inherent heterogeneity of user data, often referred to as the non-ID data problem. Unlike data in traditional centralized systems or even some other distributed settings, user data in REXs is fundamentally personal and diverse. Their preferences, rate, rating patterns, and the shared volume of their interaction history vary significantly. Some users might be data rich, while others are new or infrequent users, which would cause a cold start problem. And the heterogeneity manifests in another ways, like user interests also evolve dynamically and differently over the time. So therefore, the primary goal of client-side adaptation is to overcome these limitations. We need mechanisms that allow for the federated system to learn models tailored to the individual user's characteristics, preferences, and behaviors. Crucially, this must be achieved while still benefiting from the collaborative knowledge learned across the network and fundamentally while respecting the privacy constraints of keeping raw user data localized. This naturally leads us to the concept of personalized models within the federated setting. Client-side adaptation techniques are the specific methods we use to achieve this personalization, modifying the standard FL process to allow for local model variations tailored to each user. So before exploring more advanced adaptation techniques, it's important to recognize a baseline level of personalization inherent in many standard FedRAC architectures, particularly those are based on the matrix factorizations or embedding models. This baseline strategy relies on parameter coupling. The model's parameters are divided into two categories. And as we can see in the formula, there comes to a user embedding and item embedding. And moreover, the neural network width would also be personalized in the later parts. So let's first look more closely at personalizing the user embeddings. These factors represent the latent factors or characteristics of each user. Because they directly encode user-specific information, they are considered highly sensitive. Therefore, in this baseline approach, user embeddings are typically trained and stored exclusively on the client's device. They are never shared with the server or other clients. This provides a fundamental level of user-specific representation. As you recall, users have inherently different tastes, which causes that a one-size-fits-all model often struggles under heterogeneous data. As we just discussed, the most fundamental approach is simply training user embeddings entirely locally and never sharing them. This ensures user ID privacy, but offers limited personalization dips because the rest of the model interacting with these embeddings is typically global. We can also introduce extra protection, which I would introduce later. Take FedMF, for example. It takes the Euro federated matrix factorization setup and wraps it with homomorphic encryption for privacy preserving. In FedMF, each client factorizes its own user item data locally, updating its user latent factors right on the device, while the server only ever sees encrypted or securely aggregated item updates. Thanks to the secure aggregation, nobody can pick at an individual user's interaction history when aggregating the global model. And a more adaptive strategy involves clients downloading the aggregated global model from the server at the end of a communication round. Before participating in the next round of federated training, or sometimes purely for generating local predictions, the client performs additional training steps using only its own private data. And we are calling this process fine-tuning here simply because it works almost exactly the same way as the fine-tuning you're already familiar with. This allows the downloaded global components, which might include a shared network with, or even a globally learned initialization for user embeddings, to adapt slightly, better fitting the specific user's local data distribution. By introducing the user-specific embeddings, we acknowledge that each user is an individual task. This idea connects to the broader personalized federated learning literature, where personalization is a remedy for statistical heterogeneity. Building on this basic idea, recent research has proposed richer forms of user embedding personalization, like HPFL. It introduces a hierarchical personalization approach where user representations are learned at multiple levels, like the individual and clustered, to better adapt to privacy heterogeneity and statistical heterogeneity in user data. So the framework separates different aspects of user information, like some are shared and the others are private, and updates them with a fine-grained strategy. Federated take another direction by clustering users based on learned representations and then personalizing. In their perfect framework, each user's model is a combination of a global model, a cluster-specific model, and a local model. The user embedding in this case is enriched by the user's cluster context, like capturing commonalities with similar users, while still reflecting individual traits. Such approach show how user embedding personalization can be augmented with collaboration. Specifically, Users with similar profiles effectively inform each other's embeddings to tackle the data sparsity, always in the federated setting. Crucially, user embedding personalization is a personalization primitive. It can be integrated into many frameworks. Even when we move to more sophisticated personalization, like the items or network parameters, which would be discussed next. Most systems still retain personalized user embeddings as a baseline component. The trade-offs here are manageable. The user embeddings are relatively low-dimensional and private by nature, adding negligible communication cost because they are not uploaded, and significantly boosting poor user performance. The main caution is to ensure these embeddings don't overfit on sparse local data. Where user-specific embeddings handle who is consuming content, an emerging direction is to personalize what is being consumed, like to allow item representations themselves to vary across clients. So in traditional REXs, an item such as a movie or product or etc. is represented by a single global embedding. However, in federated settings with diverse user populations, this can be limited. On top of that, we found that personalizing items, not just the users, can really improve the performance. Intuitively, different users or user communities might perceive or interact with the same item in qualitatively different ways. Federated takes this one step further by letting each client learn its own customized item embeddings. This local offset tweaks the item representations to better fit the user's preferences. By capturing those finer-grained user item nonsense locally, it delivers noticeably better recommendation quality. But of course, there is no such thing as a free lunch. Federated keeps those custom item embeddings on every client, and that comes with a pretty heavy overhead. That is, given every client its own vector for each item, which would not fly in practice. If you look at the formula on the right, the required memory is tremendous. Even on a relatively small dataset like movie lens YM, which only have 6,000 users and more than 6,700 items, with a modest 64-dimensional embedding, there would be on the order of 1.4 billion parameters. It would cost like hundreds of megabytes just to store those vectors locally. And remember from the table on the left that the interaction sparsity exists over 95%. So most of those embeddings would never even get updated. In other words, not only would this blow out device memory limits, it would also waste capacity on items a user has never seen. That's why fully personalized item embeddings are simpler and feasible at scale, and why we must turn to more efficient alternatives like active offsets or selective personalization instead. Secondly, trying to synchronize all those personalized embeddings back to the server would create a communication bottleneck nobody could afford. Instead, the FedRAP approach uses an active personalization scheme. Each client maintains a small local offset DI on the top of a shared global embedding C. The training objective in the middle shows how it balances three terms. The Euro reconstruction rules over observed ratings, an L2 penalty to keep local offsets far from the global core, and an L1 penalty on C to enforce sparsity. This design slashes both memory and communication overhead while still capturing those fine-grained user-specific item nonsense, making personalized item embedding feasible even for large catalogs. Beyond the memory and bandwidth issues, there is a deeper problem, the data sparsity. If you look at this histogram from our recent archive study, you will see that most users have fewer than 200 interactions, and a large chunk sits in the 50 to 99 range or even less. That means the vast majority of items in a catalog are never touched by any given user. So trying to learn a full embedding for every item on device simply isn't realistic. So you would end up wasting model capacity on vectors that never get updated and risking overfitting on just a few data points. These facts together, limited memory, prohibitive communication, and insufficient local data. This would make fully personalized item embedding simply infeasible at scale. So we directly compare FedRAP L2 with the full FedRAP approach here. Both models minimize the same reconstruction rules and penalize the difference between each client's local offset DI and the global core C, but they differ in how they regularize the core embedding. So on the top row, FedRAP L2, FedRAP FedRAP L2 uses an L2 penalty on C, so the global embedding remains relatively dense. And we can see on the bottom row, the FedRAP replaces that with an L1 penalty, which would highlight here as the enforced sparsity pushes most entries of C to 0. And let's look at the heat maps. In FedRAP L2, you see lots of blue and red patches in the global C matrix, whereas in FedRAP, almost all C is 0. And the non-zero signals have moved into each client's offset DI. This sparsity in C means we only need to store and transmit a tiny core embedding, while each client captures its fine-grained item preferences in a compact local vector. The result is far lower communication and storage overhead, with no loss and often a gain, which is in the recommendation accuracy. So finally, these issues compound to make the whole approach unscalable as catalogs and user bases grow. In short, without a more efficient design, fully personalized item embeddings are simply infeasible at a real-world scale. And now let's recall pFedRAC. Unlike FedMF, which uses a mixed inner product, or FedNCF, which learns a shared score function. pFedRAC lets each client customize both the item embeddings and the scoring network itself. In practice, that means every user device holds its own copy of the score function and item embeddings, finely tuned to its interaction data. This dual personalization delivers more accurate recommendations, but as we can see, it also maintains the highest memory and communication overhead since all items remain personalized on every client. In contrast to pFederated, FedRAP streamlines personalization by splitting each client's item representation into a shared sparse core C and a compact local offset DI, rather than downloading and uploading heavyweight, fully personalized embeddings. The clients only exchange updates to the small sparse global core, drastically cutting the communication overhead. At the same time, each device retains its fine-grained user-specific offsets locally, preserving the rich personalization benefits of pFederated without its prohibitive memory and bandwidth costs. Here we see the payoff of active personalization in FedRAP, which shows in the light blue bars compared to pFederated and all other federated baselines. On every dataset, from the dense dataset like movie length 100K and 1M to the much sparser dataset like video and QB article, FedRAP delivers the highest HR and NDCG in the federated baselines and even close to the central ones. This consistent improvement across diverse data set highlights how our active personalization design strikes the right balance between global knowledge sharing and local specialization. Next is a graph-based approach. It's called gpFederated. It can personalize item representations by leveraging the user's local interaction graph. For instance, a user-specific GN might refine an item's embedding based on how it connects to other items the user has interacted with. It can capture the local contextual semantics. Another promising direction, particularly relevant for handling cold start items or leveraging rich item metadata, is to personalize the item representations based on their attributes like genre, brand, keywords, or etc. Instead of personalizing the raw item ID embedding directly, the system learns how item attributes should be weighted or combined differently for each user to form the final item representation. Here, the iFederated handles cold start items explicitly by separating the learning of item attribute representations from the modeling of user interactions, which would be personalized. The evolution in item personalization clearly shows a trend away from monolithic global embeddings towards more structured approaches. Techniques like dual views, active components, graph-based refinement, and attribute-based adaptation represent sophisticated attempts to balance the need for user-specific item semantics with the practical constraints of efficiency and the benefits of collaborative knowledge sharing. So finally, we can make the model even more personal by adjusting its weights for each user. So far, personalization has come from giving every user their own embeddings, showing what they like or how they see the items. But people also behave in very different ways. They might use rating scores differently, click at different items, browse items in their own order, and send implicit feedback like the time spent or skips. A single shared score function can't capture all those differences. To really fit each individual, we need not only custom embeddings, but also to fine-tune the parts of the network that combine user and item information when making the recommendations. So let's back to Federated. We take the client's copy of the scoring network, the with theta I here that combine user and item embeddings and fine-tune it locally on each device. This means that every user not only has their own item vectors, but also their own version of the network that process those vectors. By uploading theta I per client, pFedra captures how each person actually interacts with these items, rather than forcing everyone through the same scoring function. GPFederac adapts the aggregation logic itself to each user's behavior. First, every client trains its own item embeddings and score function on local data, then builds a small user item graph that reflects its unique interaction patterns. Next, instead of averaging embeddings across clients, the server performs a graph-guided aggregation. It uses each client's graph structure to weight and combine neighbor embeddings in a more personalized way. Finally, the server sends back this user-specific item embeddings, which the client uses together with its own model. By tailoring the GNS message passing steps to each user graph, GPFederated captures individual preferences far more accurately than just a one-size-fits-all aggregation. Next comes to the Federated. It adds another layer of personalization by giving each user their own encoder and decoder inside an autoencoder setup. On the client, there is a global encoder and a local encoder whose outputs are mixed by a small gating network that learns how much to trust each one for that user. These combined features go into a global decoder to reconstruct the user's ratings. During training, only the encoder and decoder gradings are sent back to the server and average. None of the private user-specific parameters leave the device. In such way, FedDAE captures both shared patterns via the global models and the individual information, which via the local models can be tailored network parameters to each user's unique interaction style. So with transfer FR, the key idea is to personalize only a small part of the network on each client. It keeps the big shared encoder fixed and let every device learn its own tiny adapter model. Those adapter widths are the only network parameters that users tune locally. By uploading just the adapter gradients and leaving the main encoder untouched, each client ends up with a scoring network that reflects its own data, while the bulk of the model remains common, and secure. In network parameter personalization, Each client takes parts of the model itself, rather than only its embeddings to match their own data. By customizing with instead of only embeddings, these methods can capture individual behaviors under the non-ID data with minimal extra cost. And next, we come to the server-side aggregation.